Welcome to lesson 22. So far we have learnt about the basic functioning of a PLC, we have learnt how to write a program for it, but all this time we have seen the PLC as an abstract device. We have not seen what is inside a PLC system, what actually physically makes it. So, in this lesson we are going to look at the hardware environment of the PLCs, basically what PLC systems are made of, right. So, we are going to look at components, we are going to look at components of the PLC system, their architecture, by which I mean that how they are organized, how they are connected, and their functionality, that is describing what they do. Okay. So, now let us see. Before we begin, it is customary to see the instructional objectives. So, the instructional objectives are the following. First, after going through this lesson, one should be able to mention the distinguishing features of industrial automation computational tasks. A PLC basically is a computer. So, it performs computational tasks related to industrial automation, but these tasks have certain very distinguishing features compared to the other tasks which are, let us say, done in an office environment. So, you should be able to mention some of these features, mention major hardware components of a PLC, describe major typical functional features and performance specifications for the CPU, central processing unit, IO or input output, MMI, the man machine interface, and communication modules. Okay. Then explain the advantages of a function module. So, what are the advantages of a function module? You will be able to explain, and describe some major typical function module types. So, these are the instructional objectives. So, let us start with the industrial automation tasks and their distinguishing features. So, we are going to look at the nature of industrial automation, what I call IA computation, that is computation related to industrial automation. These kind of computations, remember, that are always working on physical signals, right. So, there are temperatures and pressures and limit switch positions, starter positions, etc., which are all very physical signals, electrical in nature, which are interfaced with the PLC, and the PLC looks at its values and takes some of these as inputs and computes the output, which it computes according to some its software, for example, relay ladder logic programs. Okay. These tasks requirements are, I mean, by standards of other applications using computers, let's say digital communication or personal computing. These tasks are the computational requirement of these tasks are generally called slow, are generally, I mean, should be slow, although among themselves there could be tasks which are very slow. For example, temperature control tasks are very slow, having time constants of the order of minutes. Let us say flow control tasks would be faster, and if you have a machine control, or you have to have an actuator control, electromechanical control actions. So, in such cases the tasks are relatively faster, but even those, basically they are all made of to move an electromechanical system with a certain finite amount of power generally requires times of the order of milliseconds, or at most a fraction of a millisecond. Before that, no perceptible motion will be produced. On the other hand, these speeds are much slower compared to the speed of electronics, which we typically encounter in, let us say, communication systems. So in that sense they are slow, although within their own categories there can be fast tasks and slow or medium fast tasks or even slow tasks, right. So that is what I wanted to mean when I wrote slow fast. The complexity of these tasks are also not very complex. Some of them are very simple. Relay ladder logic diagrams are often very simple, but there could be other complicated control algorithms. There could be self-tuning algorithms which could be somewhat complicated. So I would say that the complexity of these tasks are low to medium, not highly complex. Interestingly, many of these tasks are repetitive. For example, if you take a standard process control loop, then every sampling time you have to input the controlled variable and based on your control law sense the set point and then compute the manipulated variable, right. So this computation of the manipulated variable and inputting the set point and the controlled variable goes on repetitively. So these are generally repetitive tasks and they are real time. Any computational task is called real time when there is an explicit time boundary by which this task should be completed, and this fact is actually taken into the design of the computational system which is supposed to perform this task. For example, in a control loop, whatever computation you are having, that should be completed within a sampling time. So there is an associated deadline for completing these tasks once they are started. So you in other words, even if you have a very grand control algorithm which takes a lot of time and does not complete within a sampling time, is not at all suitable, rather probably a less grand control scheme which will complete within the sampling time will be preferable, right. So in that sense they are real time. And for real time tasks one has to, because you have to also realize that within one PLC there will be several control loops working, either rungs, either they are discrete sequential control or they are analog controls, whatever it is, there are a number of control laws which have to be repetitively executed, right. So there is a requirement of determining that which should be run at what time, because some of them will have to be run, let us say, every 20 millisecond, some of them may have to be run every 500 milliseconds, some of them may have to be run every 2 minutes, right. So this is called scheduling. So there has to be a mechanism of scheduling tasks at the appropriate time so that computational resources are utilized and all the tasks are finished at before their deadlines, okay. So this is generally done using technology called scheduling, and we'll not go much into that because that's in the domain of real time systems, but generally in the case of PLCs, even when there are scheduling, PLC schedulings are generally very simple and they are static in the sense that they are the strategy which is adopted is fixed, it does not change according to situations generally. Similarly, they have very rudimentary kind of operating systems, much less generally much less sophisticated than standard other operating systems like Unix. Apart from that, but one thing is very interesting, that when you have a PLC, I mean these computational tasks are very mission critical in nature, in the sense that we do not want to have any kind of errors in them. So they should have very good reliability and they should always ensure worst case performance specifications. We cannot check average case performance specifications, like for example, if you have Ethernet, then we know that Ethernet worst case performance is generally goes down significantly compared to its average case performance. So but here, whatever technology we are using, we should generally always use worst case performance as the performance guarantee, because the consequences of a task failure could be very great, right. Lastly, often it happens that this computational environment computational tasks have to be performed at very harsh physical environments having a lot of dust, heat, moisture, vibrations and such things. So, the hardware has to be such that it is not affected by these. One has to devise proper ceilings, one has to devise proper cooling mechanisms. These are also very important in the case of industrial automation computer systems to ensure that the tasks are performed reliably and as expected. So, having said that, let us look at what makes a PLC. So, as I have said that a PLC is basically a microprocessor based system. So, as we know that a microprocessor based system will have the major components are number 1 CPU, number 2 memory, number 3 input output, number 4 power and number 5 the buses, right. So, here also you will find basically the same things. So, here you have the CPU, this is the CPU and here is the memory. As we will see, memory can be of various types and you will find you can easily make out that the PLC applications are very rich in IO, because their basic job is to interact with the physical world, right. So, you have various kinds of IO. For example, you have analog IO, you have digital IO, you have remote or sometimes called distributed IO, you also have network communication, much of it is again IO. So, you have various kinds of IO, you have man machine interface which is also a kind of IO, input output. Then you have a programmer by which you can develop a program let us say an RLL program, and you can load it into the PLC memory, that is also a kind of IO. Then you have power, you have the backplane, that this is the bus which connects the various PLC elements. Sometimes you must be knowing that sometimes you have other processors which assist the main processor. So, you could have a this is not common, this is wrong. What I meant to write is a communication processor, right. So, please correct this, by which I wanted to mean that this is a communication processor, because it has to, a PLC has to sometimes communicate with special purpose devices. So, that job is often given to a separate processor. Similarly, it could have separate input output processor, it could even have a network processor. In fact, a communication processor, part of the job is to do communication, maybe on the network environment also. Sometimes you have separate, these are actually IO which are intelligent in the sense that they have their own computing capabilities. So, one needs to, so the main CPU needs to talk to it. So, therefore, this is also a kind of IO. So, you see that a PLC is basically a microprocessor based system with a lot of IO, and we are going to see what these different types of IOs are. So, let us look at these modules at some level of depth now. Okay. So, you have a processor, a typical processor would be, I mean this is just an example, it could be 80186, it could also be from the 68000 line, various choices are available. Sometimes these processors are proprietary, not standard processors. Along with the standard processor, as I said, you could have co-processors for specific purposes like IO, like handling the programming input, etc., or managing the network. You obviously have RAM is required for running it. You have sometimes you have dual ported RAM. Dual ported RAM is RAM in which simultaneously it has 2 ports. So, it can be simultaneously written into and read from. Okay. This is important, especially when you want to read data from devices which are working without really stopping the device operation. You want to read data or you want to write data. So, you can on the fly parameterize, dump some new parameters for a PLC while the PLC is working. So, the PLC continuously uses its memory, but in between when during those brief instances when it is not using the memory, if you have a dual ported RAM, then using another processor you could write the same memory and download your parameter values in the meantime into the memory, which the PLC will use as it gets them. Okay. So, this kind of reading and writing on the fly by another processor is possible if you have dual ported RAM. You have EEPROM or E²PROM. These are typically read only memories, and they are used for storing the PLC programs. You have programmer ports which are used for downloading programs. You have network ports. You have backup battery. This is very important, because by any chance if you have power failure, you do not want, number one, your process state to be lost, number two, you do not want to lose your parameters. So, there is a backup battery always which will back up part of the RAM, and you obviously need the power supply which could be internal within the processor module, or it could be external as a separate power supply module which will connect to the processor module. It could be either way. So, let us look at a typical PLC system, a picture which will clarify the things. So, here is a typical PLC system. So, you can see that it contains multiple CPU units. Actually, these are, if you look at them, these are the various CPU units. Okay. So, these are the CPU units. Some of them are communication, some of them could be communication processors or other coprocessors. One of them will be the main processor. There are a number of rack mounted IO modules. So, these are the rack mounted IO modules, IO racks. Each one of them will plug in one particular IO card which will have various, which will interface a number of IO signals, and you have the power supply here, right. So, this is how it typically looks. You can see a number of you can see a number of ports. So, for example, you have a number of ports here, right. So, these are probably the communication processors. We can't, because they are having so many RS-232 ports, serial ports look like. There are some parallel ports, looks like printer ports. So, this is how a PLC actually looks like. There are actually, this is not the only type. PLC systems could be very large, they could be very small, everything comes into one box, that is also possible. This is a medium range kind of application. So, having looked at that, let us see how these various things are schematically connected. We just saw a diagram. So, you see that this is the scheme in which these various processors and the modules are connected. They are all connected by a bus. This is, and obviously, as you have seen that various IO modules are mounted in racks. So, there will be a ribbon cable like thing. There will be a flat cable which will act as this bus. It will connect the various modules. And sometimes these modules can even may not be situated at the on the same row. Sometimes they will be connected one after the other. Sometimes they may be connected in a cabinet which is a little distance away. So, this bus really has to extend sometimes using cables also. So, you have central processor, various kind of co-processors, I/O processor. Nowadays we are having the age of embedded processors. So some of these processors are use even DSPs. So there could be numeric co-processors or I/O processors. Generally, there are communication processors for specific communication to kinds of devices like operator stations or for communication on the network. There are various kinds of I/O modules. Some of them have processors on them, so they are called intelligent I/O. Some of them are ordinary I/O, which just takes signals and feeds it to the central processor. Plus, there are obviously memories. So this is the basic hardware architecture, which is very common for microprocessor based system. They are generally organized around a bus. Oops. And if you see inside one processor, that's also pretty standard, in the sense that you have, as you all know, that all microprocessor based systems have two kinds of buses. One kind of bus is called a data bus. Another kind of bus is called an address bus. So using address buses, we can talk to specific devices, and then we can exchange data over the data buses. So these are the data buses, connects to various devices, and these are the address buses by which the devices can be selected. You have the main processor. You have various kinds of memory. You have application memory where the computational tasks run. Even for running tasks, you need a for managing the resources of the PLC, you need some programs which are typically called systems programs. So for that you need systems program memory, you need systems data memory. You have special kinds of PLC systems are just like you must have experienced that sometimes your PC hangs. It just sits quiet doing nothing. Somehow it gets mired into some infinite kind of loop. So this is prohibited in PLC systems if due to from reasons like wrong programming to memory memory corruption. If the processor stops doing useful work, then there has to be explicit mechanisms by which the processor execution must be brought out of it and taken into a safe state. So this is typically done by watchdog timers, which are hardware devices, and sometimes they are also they are actually hardware devices. And if these timers find no proper activity over certain periods of time, then they by force take the processor to some safe state. Okay. So you could have dual ported RAMs, as I said, apart from the normal RAMs. Obviously there has to be various kinds of interfaces. Sometimes here they have shown, here we are seeing a particular another additional processor. See, this is the main processor, but we are seeing an additional processor, and the job of this processor is to interface with the programmer, so that you can, while this system is working, a PLC system is typically interfaced with a machine, and industrial machines often run continuously. So you must provide mechanisms excuse me, so that you are able to load new parameters, read status. You are able to work with the system while the system is working with the machine, so without stopping it. So for that, since not only you need a dual ported RAM, you need another processor which will talk to the programmer while the main processor is actually busy controlling the machine, right. So this is what is done. So typically these processor modules, though this is mainly a discussion on hardware, we would like to mention that typically these processor modules come with some pre-programmed software, minimal pre-programmed software. More than that, one has to develop, or one has to take from additional libraries. So you have standard things that are supported, like for example basic counting timing functions, some software up down counters, quite a few of them actually, from 0 to 999 typical value, and several timers which can time durations of the order of milliseconds to of the order of several hours or even sometimes days are available. You have various standard control algorithms already pre-coded, so that the users do not have to can easily configure their systems. The program execution in these systems is very interesting. There are generally 3-4 different types of program execution modes specified. For example, a mode could be cyclic. By cyclic we mean that you have a number of computational tasks begin just like RLL program execution. So begin here, come to the end, start all over again. So this just goes on. Typically cycle time remains more or less constant, but it could vary a little bit depending on the program logic. For example, if you have some program control statements, if then else kind of statements, then whether some block will be executed or not will actually depend on the data. So program execution time is not always constant, it actually depends on data, but roughly it will be constant, and in fact it is preferable that it is constant, so that you are not surprised that for some value of data suddenly your program execution takes a very long time and your deadlines are missed. So it is preferred that real time programs have predictable and not too much varying time requirements. So for many classes of applications, cyclic is good enough. So that is the simplest. Apart from that, you could have time controlled executions, where certain operations will start after certain times, either absolute times or relative times, that is start the pump after 30 seconds of opening the valve. This kind of controls can be executed. So exactly 30 seconds after, so this execution is timer controlled or time controlled, or it could be interrupt driven. There are some tasks which can suddenly occur, like failures kind of tasks, which once they occur they are not taken into the consideration of the regular computing flow, but once they occur they are required to have very high probability, very high priority, I am sorry, and therefore they have to immediately get the attention of the processor. So such tasks are sometimes coded in the interrupt driven execution mode. So whatever the processor was doing, it will be interrupted, and this requirement will be catered to. So but all said and done, for a given, I mean typically one must understand that typically a PLC has much less computational capability compared to a PC, although it is generally much more expensive. Or that is, if you take PLCs and PCs of the same kind of price, then you would find that the PLC is much less computationally capable compared to a normal PC which sells in the market, both in terms of memory and in terms of computing speeds. That is because price of things get actually decided by the sales volume, plus the PLC has certain other features. They are actually very rugged, and they are different kind of packaging. So all these things make this, and the third reason is that a PLC is not a is not a general purpose computer. So no one is going to download nice files from the internet and store it there, and then your emails keep piling up. Such things do not happen. So therefore memory requirements are generally well understood and much less than what is required. So therefore one keeps things only which is required, because one wants to make things reliable, and putting too many things into a machine makes it unreliable, right. So but one has to understand that these are, although they are much like PCs, in fact there are in the market the competitors of PLCs are actually called industrial PCs, which are really PCs, run on run on similar operating systems, Windows or some versions of it, but they have generally much lower computational capabilities. So we have then we look at input modules. Input modules basically convert process level signals to processor levels. So what do we mean by process level signals? Process level signals are signals which actually exist on the field. For example, they could be 24 volt DC signals or 230 volt AC signals, or even sometimes contacts, sometimes some RTD, platinum RTD, or could be a 4 to 20 milliampere current loop, the signals which actually come out of sensors, right, sensors and actuator devices. So these a PLC is an electronic device, it is actually a digital electronic device. So it as such cannot take in that kind of electrical signal, so it must convert them to processor level signals which are digital, typically 5 volt or maybe 2.5 volt, whatever. So that job is actually done by the input modules. So their job is to basically translate process level signals to processor level signals, also convert them from analog to digital sometimes, if they are not always digital. So the jobs are mainly, another important thing is to provide isolation, because the electronics, if you expose digital electronics board to 115 volt or 230 volt AC directly, chances are that it will get damaged. So you have to provide electrical or galvanic isolation using optocouplers. So input modules very often provide that. They provide fault indication, suppose some wire has broken, often they provide fault indication. This is apart from converting process level signals to processor level signals. They are generally of two types, they are either analog inputs or digital inputs. We understand the difference between them, right. So for example, a contact would be a digital input, and a platinum RTD would be an analog input. So obviously we need, for the analog input modules, we need to have analog to digital conversion, typically 12 bits accuracy, multi-channel sometimes. One input module generally supports several physical one input module supports several input channels. So there, since each digital channel actually takes 1 bit, while each analog channel could take as much as 8 or 12 bits. So therefore typically an input module will support 32, 64, 128 kind of digital input channels, while it will support 8, 16 or 32 analog channels. These are just some typical values. Similarly, sometimes it takes special inputs, like you can directly connect thermocouples, you can directly connect RTDs. So inputs can be in the form of voltage, current, resistance, etc. Sometimes it can be in the form of pulses, for example a shaft angle encoder can be sometimes connected. So this is the nature of input modules. Then we have output modules, they do the reverse, they translate processor level signals to process level signals. They are output devices, and these process level signals then go to things like motors, solenoid lamps, valves. They have to actually do work, right. So they have to be converted in form, generally they have to make, sometimes mostly they have to be made analog, or sometimes even on off kind of signals, but they have to be increased in power because they are supposed to do work, right. So they also provide isolation, and for analogs it has to provide the voltage or voltage and current drive. So typically a unit that will provide that will be a, let us say, a servo amplifier. So such amplifiers will be put on output modules. For digital output modules, sometimes they will require high power. You will just give a pulse and you will require that during the duration of the pulse there will be high current will be switched. So that such a thing will be done by the output modules. It is typically, let us say, using TRIAC or maybe an IGBT. Today one would like to probably use an IGBT. And there could also be potential free relay contacts. That is, sometimes we can do, suppose we want to switch a voltage or current, because it's digital, so it has to be on off kind of thing. So you could actually do it in two ways. One way is to use a device, electronic device which will interrupt. Another is to do a mechanical interrupter. Now since these currents can be sometimes very large, so therefore you directly from the output module you don't interrupt a large load current. You actually use a relay which activates a contactor. So, the contactor is actually a heavy device, heavy contacts, you might have seen them, and they provide contacts, and if you drive those, if you drive a signal into it, then some relay will make the contactor work. So, using a low power signal you can interrupt a high current using a contactor and relay. So, such outputs can be driven from digital output modules. So, let us have look at some of these pictures. For example, this is a typical, this is how a typical analog I/O module looks like. Let's see what it contains. So, for example, you will find that there are some analog signal terminations probably here, and there are some bus ports probably here, difficult to see this. Inside you will have, you know, these typically this is an analog, so support several channels. So, there has to be eddy conversion. Typically you do not put, if it is not that if you have 16 channels you will require 16 eddy converters, you will take one eddy converter, and the eddy converter is so fast that it will first convert this channel, then this channel, then this channel, then this channel, and so on. So, it will multiplex the eddy conversion. So, you have multiplex eddy conversion. At the same time you need to ensure that although you are taking the values one after the other, but you would like to ensure that the values that you are taking finally all belong to the same time instant in the process. So, you use xk, yk, zk, all of them are at k time instant. So, for that you need simultaneous sample and hold, where you take the value simultaneously using sample and hold circuits, and you hold them, and then the eddy converter picks them up. And you also have various output drivers, especially for output modules. So, this is the basic, these are the basic thing that an analog I/O module will contain, and of course some logic for synchronization. Then you have a different kind of I/O modules which are called distributed, or sometimes called remote I/O modules. So, these are actually intelligent field mountable I/O devices. So, you actually put the I/O module right there on the machine, and from there you draw a wire, or you connect it to a network, or you take an input output concentrator and connect several local distributed I/Os, and then make one digital communication back to the PLC. The advantages are mainly in savings in cabling costs. I might have mentioned before that cabling costs are not insignificant part of any industrial automation project. So, and they generally cause inconveniences in an industrial environment. They are difficult to maintain, sometimes may get cut, etc. So, savings in cable costs and maintenance costs are significant. Then they are sometimes, I mean, especially when they are on the network, they are actually programmable from a parameterizable from a processor or a programmer. They have, because they generally communicate with the processor over, they first of all they communicate with the processor infrequently, because they are actually intelligent themselves and they can do much of their work. Secondly, they often communicate with using digital communication protocols which are much more reliable. So, you have much improved data integrity, your cost of cable, etc. comes down. So, typically used for applications like, you know, very close positioning with analog digital encoders, which requires frequent sampling, frequent slow output generation, very difficult to do it with the central processor because it will get loaded. High speed counters, which needs to count high speed events like, you know, fast moving shafts, angle pulses. Some specific loop controllers, temperature control loop, etc., where you just need to download the set point from the central processor, and the basic loop works on the distributed I/O module. So, this main processor is not bothered with that. So, that is a distributed I/O, generally getting more and more popular now these days. Then you have some other kinds of modules called function modules. These are not, sometimes they could also be mounted on the machine and make part of a distributed I/O, but otherwise they may be situated on the PLC rack itself, but still they are actually independent modules that can execute tasks independently. So, basically reducing the central processor load. so that it needs to talk to it less often for precision and high speed tasks, and they often have their own logic, their own pre-coded control laws, they have their own optimizing abilities. It might tune its own, you just have to give it a command that you tune yourself. So it has its own code, it will actually tune a control loop. And typical application would be stepper servo control, multi-axis synchronization, as we have we will see after just following this. We will go into the manufacturing, the CNC machine controls, where we will find that there are many cases where a precise two-dimensional motion has to be created. Suppose you are actually cutting something along a surface, so you have to create precise two-dimensional motion. So you have to give motions along two axes, motion commands, and they have to be very synchronized. So that is called multi-axis synchronization. For such applications, typically you use function modules, specialized function modules, and sometimes they could be also used with distributed I/O systems to be situated on the machines themselves. This is another controller which is a valve control module. I chose this because I wanted to show the power transistors on this. So you can see the power transistors. So it has to drive. Valve means it's probably a hydraulic servo valve or something, or so it has to pull a solenoid, create some force so that the piston moves. So for that it needs to provide good amount of current. So you have these are the power transistor drives. It takes set point from outside, so it interfaces to the bus, and the central processor gives it the set point, and it has its own onboard controller, right. So this is a typical valve. This is another picture, a counter module. You can't make out much from the picture except for the fact that you can see certain things, like for example, we need to go back. So you see, you can see that, for example, this module contain I think 5 counters. So you see the count value has to be read on the bus. So these have count values have to be read, then event signals, that is go up, this thing has to come. So there are probably 5 counters here. On the other hand, it also connects to the bus so that these signals can be read. Generally used for so the count is readable on the fly because it contains dual ported RAM and high speed count. So generally used for very high speed counts. So one would have large registers and things like that. This is counter position decoder. See, most counter modules can easily be used because position decoding is often by counting the shaft angle pulses, shaft angle encoder pulses that are coming over a certain period of time, or because every pulse will mean a certain small angle rotation. So if you want to have shaft angle position decoder, it's basically counting pulses. So some of these some of these can be used for either as a counter or as a position decoder. So you have pulse inputs, you can count or you can read shaft position, and both they will be readable on the fly, as we said, and for high speed. So this is just to give you a feel of the PLC system. This is a position control module. So again, position control module, onboard dedicated high speed CPU. Position control generally requires very fast computation. So you have dedicated high speed CPU. By high speed CPU means you have CPU with higher capabilities. You used higher order processors. When you have low speed controllers, you use generally you use things like microcontrollers to realize them. Well, here you could use higher end processor like maybe 68000 and motor drive. So on the motor, so it gives there is a drive, there will be a power electronic drive which will be given a set point, and that power electronic drive will realize that set point. On the other hand, it will take its own set point, it will take from the central processor. It has digital I/O depending on what is the final motor. Various, for example, for a stepper motor, it is actually driven by digital I/O. So these are some of these modules which are used in PLC systems. It has a programmer port because you need to, there are a large number of parameters which have to be set and set point comes from the data bus. So all these modules, how they are connected, that is what are the various data paths. To understand this, you have to understand that the PLC, I am sorry this. So the PLC is, as we have said, that it's rack mounted, right. So there are a number of racks, it's like an almirah, there are a number of racks. In each rack there are slots, so in each slot you can put I/O modules or you can put CPU modules, and in each slot, so this is slot, this is rack, and in each slot contains several channels, right. So there could be 8 analog channels, so channels. So this is how I/O is actually organized. It is rack slot channel. So if you want to identify a particular physical signal, you have to have a rack slot channel addressing, which is implemented in various ways by various manufacturers. Now all these racks must be connected, so they are actually connected at this level by ribbon cables, and then from rack to rack connection is generally achieved. Okay, we will see this in the next diagram. We will see it in the next diagram. So here you are. So these are, this is one rack, let us say. This is one rack. Then you can have several racks. For example, so they are actually connected by what are known as interface units. So these are interface modules. Similarly, so you can expand your number of modules. Sometimes you can put, as I was telling, that you can put your modules in a different almirah, which is different cabinet. When I say almirah, actually it's a cabinet. So for that you need to have a special interface unit. So typically an interface unit it can be, say, typically such distance. For reliable data transmission, such distance requirements are there at a certain rate. So you can go up to something like 100 meters, which is a lot. And sometimes you can have remote interfacing, that is actually you may be having your CPU in some that is your basic PLC system in some control room, while you have these various interface units in the various shop floors, which could be even half a kilometer away and things like that. So for such cases you need special interface units which are called remote interface units. So this is the way that all these elements are actually connected with each other and buses are extended. Then all these things that are happening, one generally wants to get a view of it. So to get a view of it, you use a man-machine interface, and as such PLC modules often work without any intervention from humans. So as such they have very little MMI capability. They don't generally contain displays by themselves. They will probably contain some LEDs which will just indicate whether they are functioning normally or not. But if you want to visualize, if you want to monitor what's happening to the various variables, if you want to trend them, show it nicely to an operator, it is possible through the various man-machine interface elements. So you can have operator panels by which an operator can give commands to a variety of devices. Some of them may be mobile, it may be push button, joystick, various kinds of multifunction input panels, various kinds of things. Similarly, he can see it. You can actually connect a PC to a PLC, and on which various kinds of visualization software, which will nicely show your plant, and as I mean, levels of fluids will go up and down. It will nicely show you on the screen. So such visualization software running on PCs can be used for man-machine interfaces. Sometimes, especially for power applications, you have remote terminal units. That is, basically the system is working in, let us say, unmanned stations, and from kilometers away you want to get a view of what's happening. Let us say which of the transmission lines are on, which are off. So such a system is called a supervisory control and data acquisition system, often called SCADA. And so SCADA systems with RTUs gives operators a visualization of what is happening quite far away in unmanned places. There also MMI. They also have MMI purpose. Sometimes you have panel PCs. They are special types of PCs with touch screens, so that the operator need not type. He can just for basically convenience, because an operator has to concentrate on the process and should not be bogged down with it should be as easy for him to give commands as possible. So people use devices like touch screens in such environments. So for example, these are so there could be a variety of man-machine interface kind of devices which needs to be interfaced with a PLC, starting from operator panels to monitors to PCs to keyboards to printers. So all these it is possible to interface. Then you have to have programming devices, and this is a typical programmer. Programmers are of two types. Either they could be handheld, which you can take to the shop floor and directly program the PLC, or they could be tabletop, where you have which are of higher capabilities, and where you actually develop programs offline and maybe go and just load it there, because these have very good program development environments also. Finally, another very important thing is communication. So there are various types of communications available, as we have already told. For example, point to point, where you run direct wires from an input or output module to the actual device. There could be bus communication is actually internal to the modules, or you could be network communications, where network or remote. These we have already explained. Communication technology could be communication medium can be various. For example, it can be radio, it can be coaxial channels, it can be fiber optic cables. So different physical media may be supported, various protocols are supported. For example, RS-232, 420 milliampere current loop, for RS-482, 485. These are point to point communication protocols. Apart from that, there could be network protocols. For example, industrial Ethernets are sometimes used, where the computational requirements are well known, well understood, and that due to that is CSMACD media access protocol, you are not going to get performance is not going to degrade. You have a field bus. That's a new standard for networking in the industrial environment, which we shall be studying in much more detail. There are other less popular, probably I can call them less popular. For example, the CAN bus. The CAN bus is much more popular in another application environment, that's automobiles. Field bus is gaining popularity in the industrial environment, and some buses could be proprietary. For example, Siemens has a bus called CNEC, which is a proprietary protocol bus. The advantages of distributed network I/O are well understood. Cost saving on maintaining integrity of high speed signals, because basically the advantages of digital communication, and the advantages of having an intelligent module near the machine. So you can have good sensor diagnostics. Fault can be much more, monitoring functions can be realized without overloading the CPU. You can do special functions like startup. So in a sense, in such cases, the PLC CPU really works like a supervisory system, and the actual controls is done on the spot. So you have better centralized coordination and monitoring. So we have come to the end of the lecture, and so we have, I hope you have got a fair idea about what makes a PLC system, and as is customary, again you have some points to ponder. So think whether you can mention two distinguishing features of industrial automation tasks compared to, let us say, a task in a bank, which are also computational tasks which also communicate. Mention 5 major components of a PLC system. We have mentioned more than 5, so you should be able to mention 5, and distinguish between normal, distributed, and networked I/O. So here we end today. Thank you very much. We will meet again. So welcome to lesson 23 of the course on industrial automation and control. Today we will be talking about CNC machines, that is computer numerically controlled machines. So as usual, let us look at the instructional objectives of this lesson. So after learning the lesson, the student should be able to describe the main features of a CNC machine, what makes it, describe its main advantages, why we should spend money to buy these machines, they are very expensive. Explain the main features of part programming, because these machines are automated, they can be programmed. So the programs are called part programs. So we will see some basic features of part programming. And finally, the drives, the CNC machines create motions, all machines create motions, machines especially which are used for manufacturing. So naturally they involve drives, the technology which generates the power and the control for creating precise motion against heavy loads. So we will see these drives, and we will see the requirements on the CNC drives, so that later on when we study the drive technology, we can refer to that, and we will see how these drives are actually realized using electrical machines, power electronics, and controls. On the other hand, the workpiece is rotating generally at very high speed. It is rotating. At the same time, it can come down to actually drill a hole. So the workpiece in this case is capable of, it has a high speed rotation, and it can also move along one axis, whether the tool can move along one axis and while rotating, and the job can move have rectilinear motion, have motion, a two-dimensional motion, right.